All right, so today we're going to look at section 5.2, which is all about finding eigenvalues. Remember from last time. So we might have said something like, um, uh, if lambda is an eigenvalue, well, then AX is lambda X has a non-trivial solution. Right, so remember that x equals 0 is always a solution to this, and so we're not going to call that an eigenvector. But if we have a non-trivial x, something that's not 0, that I can plug in here, then that x is an eigenvector, and that lambda is an eigenvalue. Well, we saw this a bunch last time. I can rewrite this as a minus lambda I x equals 0, must have a non-trivial solution. But we also already discovered that when does this have a non-trivial solution? Anytime that I have a matrix M times X equals 0 and it has a non-trivial solution, well, that's the same thing as saying that the matrix itself is not invertible. Because if a matrix is invertible, then when I set mx equal to 0, the only thing that I'm going to get back is 0. Right? There's only the trivial solution. So that means that this has to be non-invertible, which is the same thing as saying that the determinant of the matrix is 0. So we're bringing a lot of stuff together in our thinking here, but it actually is a very powerful idea because, as I mentioned last time, this is actually an equation with two variables. We have an unknown x, an eigenvector, and an unknown lambda, an eigenvalue. And by thinking about this, we've actually got this down to one variable, just lambda. I take the determinant of a minus lambda I. If I set it equal to 0, and that's going to give me something that has just lambdas in it, and I don't have any x. So the idea has removed one of the variables in a sort of magical way, and we're left with a single variable lambda that then we'll be able to solve for. So let's look at what I mean by that. So in a simple case, in a 2x2 case, let's use this idea to find the eigenvalues for the matrix 2, 1, 0, 3. All right, so what we're looking at, we're looking at determinant of a minus lambda I, and we're setting that equal to 0. If I can find a lambda that makes that work, then that lambda is an eigenvalue. And so that's the determinant of a minus lambda 0, 0. Right? So because I is 1's on the diagonal, lambda I is lambda's on the diagonal, I need to set that equal to 0. Well, that's the determinant of 2, 1, 0, 3 minus lambda 0, 0 lambda has to equal 0, which is the determinant of 2 minus lambda, and really we're going to be able to jump right to this step in general, 0, 1, 3 minus lambda. And so again, what do? We just, since I say a minus lambda I, this lambda I is lambdas on the diagonal, so when I subtracted lambdas off of all of the diagonal entries. And this is really where we'll start. This is just extra stuff in the middle, some very detailed steps, but we can really get right to here. We know how to take the determinant of a 2x2 matrix. The determinant of a 2x2 matrix we get by going down the first diagonal and subtracting what we get off the second diagonal. And so that is 2 minus lambda times 3 minus lambda minus 0 times 1. And that still has to equal 0. And so that's 2 minus lambda, 3 minus lambda equals 0, which says that 2 is lambda, or 3 is lambda. And I get two separate eigenvalues from the matrix, which, keep in mind, in this simple case, really just were the diagonal elements of that matrix because the matrix was triangular, that is, had only zeros below the diagonal. Right, so let's apply this in a bit of a trickier case. Let's look at 2, 1, minus 1, 3. So we're going to look at A minus lambda I, which is 2 minus lambda, 1, minus 1, 3 minus lambda. We're going to take its determinant, and we get 2 minus lambda, 3 minus lambda, minus negative 1, which is 2 minus lambda, 3 minus lambda, plus 1. And now our goal is to set that equal to 0, because we're looking to see when this is equal to 0, because that corresponds to a non-trivial solution. So we need to set this equation, or that expression. So 2 minus lambda, 3 minus lambda, plus 1. We need to set that equal to 0. This one we should be able to see without too much trouble what we got to do. Right? This is really just a quadratic. Lambda is our variable, so this is a quadratic. We're going to have to FOIL, recombine with this 1. Hopefully, FOIL, factor again. If not, we got to use a quadratic formula. So when we expand, we get 6 minus 2 lambda minus 3 lambda is minus 5 lambda, plus lambda squared plus 1 is 0. So that's lambda squared minus 5 lambda plus 7 is 0. There's no way to refactor that. But I can say that lambda is, by the quadratic formula, negative b plus or minus the square root of b squared minus 4ac, which is minus 28, all divided by 2. Now notice what happens in this case, right? So this is a negative under our square root. So we actually get what we're going to call, these are complex eigenvalues. We're going to talk about these more in a later section. But for right now, we have no real eigenvalues. Right, so no real eigenvalues because we get a negative under the square root. And that can happen. Right, so we can think about a simple situation where that might happen. Remember, eigenvalues, well, so suppose that I had a matrix which just rotated. If I rotated everything in the plane around, well then there's no vectors which, after I rotate, are multiples of where we started. So there are no eigenvectors, so there are no eigenvalues. And this matrix that we started with is going to be something that's similar to that. It might be a rotate and some sort of other crunching around. But if we have any sort of rotation involved, then nothing can be a multiple of what we started with because everything is rotated away from where it started. All right, so let's look at some more. All right, so let's look at another one. We're going to go with the 3 by 3 matrix this time. Let's look at this matrix A, which is 3, 0, 0, minus 1, 2, 1, 0, 2, 4. And let's look at, let's say, can we find any eigenvalues of this matrix? All right, so remember what we're looking at is we're looking at the determinant of A minus lambda I. So that's what we want to do. So that's the determinant of 3 minus lambda, 0, 0, minus 1, 2, 1, 2 minus lambda, 1, 0, 2, 4 minus lambda. So that's what we're looking at. Now we need to take the determinant. But this is now a 3 by 3 matrix, and taking the determinant of those can be a lot trickier. Although we're in luck, because in this case, we have a row with a lot of zeros, which means that we can apply a cofactor expansion for the determinant along row 1, because zeros make for very nice determinant calculations. So if I apply a cofactor expansion along row 1, what I get is 3 minus lambda times the determinant of the remaining matrix, 2 minus lambda 1, 2, 4 minus lambda. And then minus 0 and plus 0 for our other two pieces, which is 3 minus lambda times 2 minus lambda times 4 minus lambda minus 2. If I take this and this. And so now what we have is we have, let's come up here. We have our determinant. Notice what it is now, right? So now it's actually a degree 3 polynomial. If I would expand this out, it becomes a quadratic in here, and it becomes a cubic if we include this. So this thing is actually called the characteristic polynomial. Right, we always get a polynomial when we take the determinant of a minus lambda I, and that polynomial is called the characteristic polynomial. Let's keep on expanding this or trying to simplify this. 3 minus lambda, the middle becomes 8. That's minus 2 lambda, minus 4 lambda is minus 6 lambda, plus lambda squared, minus 2. Which is 3 minus lambda, lambda squared, minus 6 lambda, plus 6. Now remember, our goal is to set this equal to 0. So what we got is 3 minus lambda, lambda squared, minus 6 lambda plus 6 equal to 0. We could push this through and expand it and get a cubic, but there's really no reason to do so, because what we're interested in when we set this equal to 0 is to factor as much as possible. And so we already have this one piece out here. And this says that lambda is 3 is an eigenvalue. Now this one I try to factor if I could, but I can't. And so I can't factor this, so I have to use the quadratic formula. 6 plus or minus the square root of d squared, which is 36, minus 4ac, minus 24, all over 2a, which is 6 plus or minus the square root of 12 over 2. Well, but 12 is 4 times 3, so that's 6 plus or minus 2 root 3 over 2, which is 3 plus or minus root 3. So we get 3 eigenvalues. 3, 3 plus root 3, and 3 minus root 3. Those are our 3 eigenvalues for the matrix that we began. Let's look at another one. Okay, suppose that this is our matrix. Let's find the characteristic polynomial and therefore the eigenvalues corresponding to this particular matrix. All right, so anytime we're looking at a minus lambda I and taking its determinant, and that's the determinant of 1 minus lambda, 0, minus 1, 0, 2 minus lambda, 0, 0, minus 1, 3 minus lambda. So that's what we're looking at. If we're taking the determinant, we're looking for any row or column that has lots of zeros. And I have two choices here. I could either use this first column or I could use the second row. Let's just go with the first column. If we're using the first column, then we're starting with a positive. Remember, if we would have used the second row, we started with a negative because we started at the second, even. But we'll go down the first column, and I get 1 minus lambda times the determinant of the inside pieces, which is 2 minus lambda, 0 minus 1, 3 minus lambda, which is 1 minus lambda, 2 minus lambda times 3 minus lambda, minus 0. And this is a particularly simple case where there's nothing else we have to do here, because we have a cubic, but it's already all the way factored. One piece, one piece, one piece. And I can say immediately that the eigenvalues are lambda equals 1, lambda equals 2, and lambda equals 3. All right. Let's look at one more and go a little bit further with it. All right. So this is going to be our matrix. Again, let's find the characteristic polynomial. And any eigenvalues. But then after that, for this one, let's also find a basis for each eigenspace. This is something that came from last time, and we'll see how to do that. All right, so we'll start with just the characteristic polynomial and eigenvalues. So if we wanted the characteristic polynomial, we're looking at a minus lambda I and finding its determinant. And so this is the determinant of 3 minus lambda, 0, 0, minus 3, 9 minus lambda, 0, 0, 3, 3 minus lambda. Well, this one is going to be fairly simple. We're going to do a cofactor expansion across the top row, and we see 3 minus lambda times the determinant of this, the leftover piece, which is 9 minus lambda, 0, 3, 3 minus lambda. I want to keep a hold of our matrix, so I'm going to rewrite it up here. And so this becomes 3 minus lambda times 9 minus lambda times 3 minus lambda by going down here, but then minus 0. And so this is our characteristic polynomial. So if we set it equal to 0, we see that 3 is lambda, or 9 is lambda, or 3 is lambda. And so this can happen where I get the same eigenvalue showing up as 2 different factors of our characteristic polynomial. So I'm still just going to write 3 or 9 as my eigenvalues. Those are my eigenvalues. But let's find eigenvectors that correspond to each of those. We'll start with 9. And let's remember how to do that. How do I get an eigenvector corresponding to a particular eigenvalue? Well, if I want an eigenvector, I'm looking at ax is lambda x. So I'm looking at a minus 9I times x is equal to 0. Well, a minus 9I, in this case, if I take 9 off the diagonals, becomes minus 6, 0, 0, minus 3, 0, 0, 0, 3, minus 6. So I just subtracted 9 off the diagonals. Now we're going to row reduce this matrix. If I row reduce this matrix, this is what we get. we get 1, 0, 0, 0, 1 minus 2, 0, 0, 0. And you can put that into your calculator if you like, but that's what we're going to get when we row reduce this matrix. So, but remember, what we're really looking for is this times x equals 0. So we're really looking at this as a system of equations with 0 on the right-hand side. And this, and we have one free variable in this case. X3 is our only free variable. So this reads x1 is 0, x2 is 2x3, and x3 is free. So this is the same thing as saying 0 for x1, 2x3 for x2, and then 1x3 for x3. So a basis for the eigenspace corresponding to lambda equal 9. This was all lambda equal 9. Basis for the eigenspace is the vector 0, 2, 1. So we pull off this vector, and that's our basis for corresponding to the eigenspace for the eigenvalue lambda equal 9. All right, let's look at 3. For lambda equal 3, what happens? We're looking at a minus 3i. A minus 3i is 0, 0, 0, minus 3, 6, 0, 0, 0, 0, 3, 0. Okay, so let's see what happens. If we row reduce this matrix, what we're going to end up with is, let's just put this one in our calculator to make sure. One, 0, 0, 0, 1, 0, 0, 0, 0. So what we end up in this case is still one free variable, and so this looks like this. Our free variable is still x3, but this reads x1 is 0, x2 is 0, and x3 is free. So that's x3 times 0, 0, 1, and our basis for the eigenspace is 0, 0, 1. So this is the eigenvector, and only one eigenvector corresponding to lambda equals 3. Okay, so how about this one? This one is going to be a 3 by 3. All right, so we have to do exactly the same thing. If this is our matrix A, we're going to look at A minus lambda I. This one's going to be a little bit more complicated though. So if I take A minus lambda I, I'm going to get 3 minus lambda, 1, 1, 1, 3 minus lambda, 1, 1, 1, 3 minus lambda. Our lambdas come off all of the diagonal elements. And then I need to take the determinant. And this is not nearly as easy to do in a 3 by 3 case. Now, we can apply the determinant by a cofactor expansion. If there's a bunch of zeros, then that's usually a nice thing to do. We can also apply our second trick of taking a determinant of a 3 by 3 matrix and rewrite our first two columns. And then think about this diagonal, the diagonal trick here. So if I go down, I get 3 minus lambda cubed. If I go down, I get, oops, what do we get? That actually belongs to this. So I get 1 times 1 times 1, and then I get 1 times 1 times 1 here. Coming this direction, gets 1 times 3 minus lambda times 1. 1 times 1 times 3 minus lambda, and then 3 minus lambda times 1 times 1. So the downwards are 3 minus lambda cubed plus 1 plus 1, and then subtract the upwards, which are 3 minus lambda plus 3 minus lambda plus 3 minus lambda. And so we can simplify this a little bit to start. 3 minus lambda cubed. This is 3 times 3 minus lambda, so that's minus 3 times 3 minus lambda plus 1. Plus 2. There's 2 there. Okay, and so now we have to be clever. And say, in general, when we get to this point, we've got a polynomial, but it's going to be a big, long polynomial. If we had a 4 by 4 or a 5 by 5, we'd have a larger degree polynomial. So this is always going to be a polynomial. We always look to find the roots, the zeros of this polynomial, because we've got to set this equal to 0. Right, that's always what we're looking to do. This thing here is called the characteristic polynomial. For the matrix that we started with. And so this one's a little bit tricky because it's a cubic. So it's tough to see what's going on here. Right? But so what we're going to do with this one is we're just going to expand everything out and see what we can see. All right, so if we expand this out, then what we're going to get is, let's just do one piece at a time. 9 minus 6 lambda plus lambda squared, all times 3 minus lambda, so I just did 2 of them, minus 9 plus 3 lambda plus 2 is 0. If we push these through, then I get 27. I get minus 18 lambda. I get plus lambda cubed. That's from pushing the 3 through. And then I push the lambda through, makes minus 9 lambda plus 6 lambda squared. Minus lambda cubed. So this wasn't a lambda cubed right here. This was a 3 lambda squared. It's supposed to be 3 lambda squared. Okay, minus 9 lambda plus 6 lambda squared minus lambda cubed. Good. Minus 9 plus 3 lambda plus 2 is 0. We combine our like terms together. We see a minus lambda cubed. Our lambda squared, we got 2 of them. That's a plus 9 lambda squared. Our lambdas, we have minus 18 and minus 9 is minus 27. And then this makes minus 24 lambda. And then our constants are 27 and minus 9 is 18. So plus 20 is equal to 0. So this characteristic polynomial, again, is very tricky to actually solve and figure out what the solutions are. And so in that case, when we get to a cubic, if it's a cubic which is not already, at least has a factor with it, I'm going to just give you what the values are, the values for lambda are, so that we can actually continue to work with it. And so my claim here, although it's not obvious how you would actually get to this, my claim is that the actual values, the roots of this equation, are 5, 2, and 2. If I would take x minus 5, x minus 2, x minus 2, and set it equal to 0, we get exactly this same. And let's just make sure that that's the case. Right, so if I, these are lambdas, not x's. If I would FOIL the first two, then I get lambda squared. I do need a minus sign all the way out front as well. I get lambda squared times minus 2 lambda and minus 5 lambda is minus 7 lambda, and then plus 10, all times lambda minus 2. And this is lambda cubed, let's do this one through, lambda cubed minus 7 lambda squared plus 10 lambda. And then when I put this one through, I get minus 2 lambda squared. I get plus 2 lambda. Okay, wait a minute. I get minus 2 lambda squared. I get 14 to plus 14 lambda, and I get minus 20. And now if we combine our like terms, I get minus my lambda cubed, or that was supposed to be a lambda cubed right there. Sorry about that. That was lambda times lambda squared is lambda cubed. So I get the lambda cubed. My lambda squareds are minus 9 of them. My lambdas are 24 of them. And then minus 20, which is exactly the same thing as we have down here when we push the minus sign all the way through. So in fact, this 5, 2, and 2 does work. These are the roots of that polynomial. All right, so let's keep that in mind. 5, 2, and 2. 5 and 2 are our eigenvalues. Let's remember what our original matrix was. 3, 1, 1, 1, 3, 1, 1, 1, 3. That's our original matrix. Let's also go back and find the eigenvectors, or a basis for each eigenspace. Let's start with the one that just had a single occurrence in the characteristic polynomial. So let's look at lambda equal 5. So if we look at lambda equal 5, so this becomes a minus 5i, which is negative 2, 1, 1, 0, negative 1, negative 2, 1, 1, 1, negative 2. So that's what this looks like. Let's row reduce this matrix, because we're setting that equal to 0. If we do that, what we get is 1, 0, 0, 0, 1, 0, minus 1, minus 1, 0. So that's the reduced row echelon form of that matrix. Remember what we're doing is setting it equal to 0. So we're thinking about this as a system with 0, 0, 0. So x1, x2, x3. This reads x1 minus x3 is 0. x2 minus x3 is 0. x3 is free, which is at x1. So this becomes my vector x is x3, x3, if I bring all of those over, and then x3 is x3, which is x3 times 1, 1, 1. So 1, 1, 1 is the eigenvector corresponding to lambda equal 5, and it is the basis for the eigenspace corresponding to lambda equal 5. It's a one-dimensional eigenspace because there's only one free variable. Let's look at lambda equal to 2. If lambda is 2, then a minus 2i is 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, this row reduces to 1, 1, 1, and then 0, 0, 0, 0, 0, 0. So we're really looking at 1, 1, 1, zeros everywhere else, and then zeros.
And this corresponds to the system of equations x1 plus x2 plus x3 is 0, x2 and x3 are free. So if we use this to come up with the vector, so if we turn this into parametric form, this becomes x1 is negative x2 minus x3, and x2 and x3 are free. Okay, so but this corresponds to the vector x, x1, x2, x3, which is negative x2 minus x3, x2, x3. And remember that we need to break this up into two vectors because we have two free variables. And this is negative x2, x2, 0, plus negative x3, 0, x3, finally giving us x2 times minus 1, 1, 0, plus x3 times minus 1, 0, 1. And so we get two eigenvectors corresponding to lambda equals 2. So what I can say is that the eigenspace for lambda equals 2 is the span of these two vectors, minus 1, 1, 0, and minus 1, 0, 1. So this is a two-dimensional eigenspace, a two-dimensional subspace of R2 that makes a plane, right? Because we got the span of two vectors. So this happened because lambda equals 2 showed up as two solutions. It showed up as a double root for our characteristic equation. That doesn't always mean that we'll have a two-dimensional eigenspace, but it means that that's certainly possible. Okay, and so that's what we've got from this section. We'll see you next time.